In this video, we'll talk about separable equations, which is our first type of equation we can actually solve directly and get a large class of equations that we know how to find the solution. So this first type of equation we're going to look at are ones that can be solved by direct integration. Some of these work easier than others, but the idea is mostly the same. I want to get to something that I can just do an integral and solve a first-order differential equation. We've seen some of these before, namely things like this one that we did last time, dy dt equals t squared. Right? We can just solve this out. Right? I can integrate both sides. I know if I integrate dy dt in t, this is going to give me just the function y back, because that's the fundamental theorem of calculus. If I integrate the derivative, I get the function back. I can also integrate t squared in t and get me t cubed over 3 plus a constant, giving my solution here being y of t is t cubed over 3 plus c. That's my general solution, and if I had initial condition, I could then use it to find the c value. And so clearly this idea will work as long as the right-hand side here is only a function of t. The process being you integrate both sides in t. One goes to y by the fundamental theorem of calculus, the other goes to a function that we can find, and that gives you your answer. Now, is this all this will work for? Well, the answer here is no. What if things are more complicated? Well, we can tie this back to the differential that we learned about in Calc 1 and work from there, right? The point is, when you do integrals, you need a differential to compute an integral. This is the dt, the dx, the dy that show up at the end of the integrals. You need that there, otherwise the integral doesn't make any sense. For the last example, we could just sort of put it on both sides because we had a dy dt on one side that we knew was going to integrate to a nice thing by the fundamental theorem of calculus. The other way we can think of this is via the actual differential from before. And how is this defined? Well, if we have a function y of t, then the differential dy is defined as dy is y prime times another differential dt. Right, this is changing variables when you use substitution, a whole bunch of other things. But what it really means is that in a formal way, we can in fact split up this derivative as a quotient of two differentials and put one on each side. I'm allowed to replace the dy dt derivative by the differential dy divided by differential dt and manipulate those things separately. That's going to allow me to do more complicated things. Right? I can then visualize, like last example we had, if I have dy dt as t squared, I can rewrite this by moving the differential to the other side as dy equals t squared dt, and then I'm just going to integrate both sides directly. Integrating dy gets me y as it should. Integrating t squared dt gets me a t cubed over 3 plus c, and I'm right back to the answer that I had before. So where does this lead us? This leads to the definition of a separable equation, which is what we need to make this process work in a more complicated scenario. So we say the differential equation dy dt is f of ty is said to be separable if I can write it as some function g of y times dy dt equals some function h of t. Basically, if I can separate the variables to put the y's on one side and the t's on the other, that's why it's separable. If I can split them into two separate sides, we call it separable, and that's going to make things work. Because we can also write this as g of y times dy equals h of t times dt by moving the differential like we talked about before. And this makes us home free, basically, for these types of problems. The point is, once I can write the equation in this form, I can then integrate both sides. One integral will be in y, one will be in t, but that's entirely fine. I'm computing the integral of both sides of an equation. I'll get the same thing up to a plus c. And I will only need one plus c because I'll be able to combine them together into one single constant. You can go on either side of the equation, that's also fine. This generally will not leave you with an explicit solution of y equals something else, and that's also entirely fine. All right, let's see an example of one of these. So I have here dy dt equals y times t. So I need to get the y's onto the left-hand side, leaving the t's on the right. And for this one, it works out okay. I get to a 1 over y dy dt equals a t, or 1 over y dy equals t dt. I can then integrate both sides. That will give me a log of absolute value of y on the left, and a t squared over 2 plus c on the right. I decided to put the c on the right here, but you can do it either way, it's fine. This would work for an implicit solution, but in this case, I can solve out for y. Let's go ahead and do that. I can exponentiate both sides. I will get that y is e to the t squared over 2 plus c. or as I more commonly see this written, I can rewrite this as a d times e to the t squared over 2, for d, the constant, being e to the c. So this here would be my general solution to this problem. And we can check if I differentiate this, I get that dy dt is going to be a 2t over 2 times a d e to the t squared over 2 by the chain rule, which is exactly t times y, was the equation we started with in the first place. That's the idea of a separable equation, how you can use direct integration to find solutions to these types of problems when the variables work out as nicely as they do, to put the y's on one side and the t's on the other.